So for this problem, we have to find a vector equation for a line that intersects two planes. And so we've been supplied with the equations for these two planes. And one is 2x minus 5y plus 3z equals 12, and we have the other one as well. Now, the trick to solving these kinds of problems is to really, with linear algebra, if you can imagine what's happening in your head, the question becomes quite simple. And so a plane, but what is meant by a plane is it's essentially just like a piece of paper. You can fold it in any one direction. Like here would be a piece of paper, and it's intersecting another piece of paper. And we have to find an equation that describes that. And so here I've written a Cartesian vector form for the two planes, and we can kind of get a sense of how they're oriented in three-dimensional space. So to understand this question, we have to know what is the line that intersects two planes. So if we go down, then here's the planes. The line that intersects the planes is this one here. This yellow line intersects both planes. And so when they're asking for an equation for the line that intersects two planes, we're saying that, hey, if I stuck this piece of paper through another piece of paper, that line that runs through both of them, that would be the line that is the intersection. And so to do this, we have to have, there's two requirements. There's two requirements to solving this. One is that we have a point that we can center on. So we need a point to center. And then from that point, let's use this white point here. From this white point, we need a direction to go. And so since we know that the line of intersection is this yellow line here, then if we had a vector in that direction and we had a point to center it on, because vectors normally, if we had an xy graph, this is terrible, 1 second here. If we have a xy coordinate system, a vector could be here, but that same vector could also be here. So this is why we take a point to center it on, but then we also need a vector in the right direction. And so let's go over how to find, first off, a vector in the right direction. Well, the way we do this is we draw the normal lines. Now the normal lines are perpendicular to the planes. For instance, this blue normal line is directly perpendicular to this blue plane. And so we draw that, and we can take the green normal as well, and that is just directly 90 degrees to the plane. Now, by taking the cross product, if we have the green normal here, as we saw in the line just underneath here, then the cross product returns a vector that's perpendicular to the two normal vectors. So if we're going up and we're going sideways here, then the cross product is in the direction of the line. So we can just say that the line that intersects the two planes is the cross product of the two equations for the planes. So if we take the cross product, we've solved one of the requirements. We have that vector in the right direction. And then we only need to solve a point after that. And we can actually do that by using the vector that we get. So let's start by calculating the cross product. So we have vector A, and we're going to take the cross product of A cross B. And so this gives us 2, -5, 3, and I'll just erase this here. And then we're going to take the cross product of that with 3, 4, -3. Well, I think I've inverted the colors here because this green one is actually the blue numbers here. But anyway, now if you have problems calculating the cross product, I've made another video on a method of how to do that. So I won't go over that in this video, but to take the cross product, let's take, so we have 15 minus 12, and that'll give us 9 minus plus 6, and 8, well, this is going to be plus again too, 8 plus 15. And so our cross product equals, now we have x, y, and z coordinates. So this will be 3, this will be 15, and then we'll also get 23 here. So this cross product is the equation for this line here. It is the line that gives us the direction of the intersection. And so now all we need to do is find a point that somewhere on here that we can start that vector at. And so the thing about the two planes is that if we know that they intersect at some point, then at some point one of these variables, whether it be the x, z, or y, one of those will be the same. So we can just say that at some point we know that both x's will have to equal 0. So what we do is we substitute a 0 in for x. So what we do is we have 2x minus 5y plus 3z equals 12. So now we're going to say that x equals 0. That's what we're going to center our point on, x equals 0. And then using these equations, we can find out what those other coordinates would be. So x equals 0, which means that the equation for a then becomes, because it's going to be 2 times 0, so we just don't even have to worry about it. And that means that we get negative 5y plus 3z equals 12. And then for b, what we get is it's 3 times 0, so we'll just go 4y minus 3z equals 6. Now, I'll just erase this here so I have some space. Now, what we can do is, so this isn't 16, sorry, this is 12, equals 12. Now, because this 6 is directly half of 12, if we just double these values, we would say that since negative 5y plus 3z equals 12, then if we take 2 times 4 and 2 times negative 3 and 2 times 6, then that is going to equal 12. So we could just say that it's going to equal 8y minus 6z. And then using this, we can just algebraically solve in terms of one of the variables. Now we're just simply doing, see, now we have 2 equations and only 2 unknowns. So it's very easy to solve because we've decided that we're going to center that point at x equals 0. So then we get, if we take we'll take the 6's over, so we have plus 6z, and we'll take this over, so we're going plus 5y, and then that leaves us with 9z equals, let's see here, 13y. And then we can say that z equals 13 divided by 9 times y, and y equals, let's see, we have z times 9 divided by 13. So using this, we can substitute in and algebraically solve to find out that by putting this into these equations, we return that, let's see here, what will y equal? Y equals negative 18. I'm not going to go through the whole algebraic solving for this. Then z equals negative 26, and x we decided was going to be 0. Now, we can do this for y. We can say we're going to center it at y equals 0 or z equals 0, and then we solve in terms of these variables. But given this equation, none of them are going to be 0 at the same time. So what this does is now we have our point centered and we have our cross product. We can put this in parametric form, and that describes the vector equation. So the line that describes it, I'll call it R, we simply write as the point we want to center it at, which is 0, negative 18, negative 26, plus t times 3, 15, 23. I think I'm cutting off the screen here. So 3, 15, 23, this was our cross product. cross product. And this was our point to be centered. Center point. And so what this is saying is that for any value of t, if we put in 100t, then what we're saying is that that vector will continue out really far. If we put in 2t, then maybe the vector only comes out to, just over here. It's slightly off center. And we can say that if this plane expands infinitely wide, then putting an infinite t in will just mean that this line continues forever. And so if we didn't have the center point, we just wouldn't know where that vector started. And that's why we need both. So parametric form preserves both so that we still have our center point and our cross product. And so really it just comes down to being able to visualize this in your head. And it really becomes quite easy after you do this once or twice.